So let's proceed on symmetries and group of permutation. Symmetries and groups of permutation. A symmetry of a geometrical figure is a rearrangement of the figure that A preserves distances and angles between points of the figure and B leaves the appearance and location of the figure unchanged. So for example, a 60 degrees rotation counterclockwise of a regular hexagon as shown below results to the function R sub 60 contains AB, BC, CD, DE, EF, and FA. So those are the elements of counterclockwise of a regular hexagon. So it is the 60 degrees rotation of a regular hexagon. So is R sub 60 a one-to-one function? Yes, it is one-to-one function. Is R sub 60 onto function? Yes, because all of the elements of the codomain have a pair of the element a domain. So range is equivalent of codomain. So notation for symmetries. The function R sub 60 of a regular hexagon can also be written in a table form. So with this form, we can directly determine if it is one-to-one and onto or not. So R sub 60 is written by contains AB, BC, CD, DE, EF, and FA. Composition force of symmetries. So suppose we want to find for R sub 60 of R1 where R1 is the reflection about the axis through vertex A. So we get that if we have the reflection about the axis through vertex A, so suppose that it is the mirror, then BF will be going to FB and CE is EC. So reflection through vertex. So in table form, we have A takes A and sends it to A. Takes B and sends it to F. Takes C and sends it to E. So takes D and send it to D. Takes E and send it to C. Takes F and send it to B. So the composition of R60 of R1 can be found using permutation, that is, so it is the original, then it is the reflection of about the axis through its vertex. So A maps to A maps to B, the results is B. B maps to F, F maps to A, then the results is A. C maps to E, E maps to F, the results is F. D maps to D, D maps to E, the results is E. E maps to C, C maps to D, the results is B. F maps to B, B maps to C, the results is C. Remember, you apply the permutation right to left, just like composing functions. So, R60 of R1 contains A maps to B, B maps to A, C maps to F, D maps to E, E maps to D, F maps to C. If G is an empty subset of S, we say that G is a group of permutation. If the following conditions hold, if sigma, tau is an element of G, then tau of sigma is an element of G. There exists an identity element of G. So in our tree, if sigma is an element of G, there exists an inverse element of G. Theorem, a permutation of a set A is a function, P function A maps to A, that is both 1 to 1 and onto. Then, if it is 1 to 1 and onto, bijection. A function composition is a binary operation called permutation, multiplication, and the collection of all permutation of a set A. So the permutation of sigma of tau is given by sigma of tau of A. So it is all equal. So let's have an exercises. So A, suppose that A is a set of 1, 2, 3, 4. Let sigma contains 1, 3, 2, 5, 3, 4, 4, 1, 5, 2. And tau contains 1, 2, 2, 3, 3, 1, 4, 5, 5, 4. So use the definition of permutation to compute for the following. So I will be the one to answer number 1 to 3 and the rest will be answered by you class. Then after you answer, I will call someone to answer it here. So we have tau of sigma 3. So sigma of 3 to 4, 3 maps to 4, and 4 maps to 5. So the answer is 5. So number 2, sigma squared of tau. First, we are going to write 1, 2, 3, 4, 5 on the top. So 1, 2, 3, 4, 5. So 1 maps to 2, squared of the sigma is squared, so 2 times 1 maps to 2, 2 maps to 5, 5 maps to 2. So the result is 2. 2 maps to 3, 3 maps to 4, 4 maps to 1. 3 maps to 1, 1 maps to 3, 3 maps to 4. 4 maps to 5, 5 maps to 2, 2 maps to 5. 5 maps to 4, 4 maps to 1, 1 maps to 3. So, sigma squared of tau contains 1 maps to 2, 2 maps to 1, 3 maps to 4, 4 maps to 5, 5 maps to 3. So, in our number 3, tau of sigma. So, sigma, 1 maps to 3, 3 maps to 1. 2 maps to 5, 5 maps to 4. 3 maps to 4, 4 maps to 5. 4 maps to 1, 1 maps to 2. 5 maps to 2, 2 maps to 3. So, tau of sigma contains 1 maps to 1, 2 maps to 4, 3 maps to 5, 4 maps to 2, 5 maps to 3. So, 3. So, in our number 4, will be answered by Miss J. Number 5, Mr. MJ. Number 6, Miss Jen. Number 7, Miss Marge. And in our number 1 here, will be answered by Miss Mela. And our number 2 will be answered by Mr. Jose. And in our number 3 will be answered by Mr. Kirk. Let's see if your answer is correct. So, in our number 4, tau of sigma. Sigma of 4 maps to 1, 1 maps to 2. Then, correct. Number 5, tau, 5 maps to 4, 4 maps to 1. Correct. Then, in our sigma of, to the 4th power, then, of tau, 1 maps to 2, 2 maps to 5, 5 maps to 2, 2 maps to 5, 5 maps to 2. 2 maps to 3, 3 maps to 4, 4 maps to 1, 1 maps to 3, 3 maps to 4. Check. 3 maps to 1, 1 maps to 3, 3 maps to 4, 4 maps to 1, 1, check. 4 maps to 5, 5 maps to 2, 2 maps to 5, 5 maps to 2, 2 maps to 5, check. 5 maps to 4, 4 maps to 1, 1 maps to 3, 3 maps to 4, 4 maps to 1, check. Then in our number 7, we have tau to the 3rd power and sigma to the squared. So, 1 maps to 3, 3 maps to 4, 4 maps to 5, 5 maps to 4, 4 maps to 5. Then correct. So, it is correct, number 7. So, in our number 1 here, we have the sigma, the tau, and the mu. So, we need to find the sigma squared, mu squared, tau squared. So, first, let's have tau. So, 1 maps to 2, 2 maps to 3, 3 maps to 4, 4 maps to 5, 5 maps to 2, 2 maps to 5. Then, correct. So, 2 maps to 3, 3 maps to 5, 5 maps to 3, 3 maps to 4, 4 maps to 1, 1 maps to 3. So, number 1 is correct. So, in our mu, So let's see if it is in the 6 elements. So 1, 2, 3, 4, 5, 6. Then the last is the identity element. So it is correct. So in our mu raised to 176. So if you see like this class, all you need to do is to get the modulo. So 176 divided by 6, you will compute only and 176 minus 6, and what you get if you divide 176 to 6, then we got the 2. So 1, 2 in our mu. So 1, 2, so 1 ups to 1, 2 ups to 2, so 1, 2, 5, 4, 6. So number 3 is correct. So that's our discussion all about relations, abelian group, and permutation. Thank you for listening.